Hello, my name is Imma Curato and this is my talk for the Bernoulli IMS One-Word Symposium. I will talk today about inheritance of strong mixing and weak dependence under renewal sampling. This is a paper I wrote in collaboration with two of my colleagues at University, Dirk Brandes and Robert Stelzer. The motivation for our work starts by the following observation. Let us assume to work with a strictly stationary process X and that we have an equidistant sample of the process, namely xn, where n belongs to the set of the natural integers. If we have further information regarding the asymptotic dependent structure of the process X, so we know that X is weakly dependent or strongly mixing, then we find in the literature a very general asymptotic theory that covers all the sample moment asymptotics, mostly of the process X. When you read the literature, however, if you, for example, would like to obtain general asymptotic Riemann result for the sample moment statistics of the process X by using a random sample, X capital Tn, where n goes in n, you don't find in the literature results that have a general flavor. We try in this work to cover this gap in the literature. More specifically, we focus on renewal sampling schemes that they are defined by means of an inter-arrival time sequence tau, that is non-negative sequence of independent and identically distributed random variables with distribution function mu such that mu0 is strictly less than 1. For E in the set of the integer z, we can then define a capital T as follows. We call this sequence a renewal sampling sequence. In particular, we will focus on analyzing the asymptotic dependent structure of a process that we call capital Y in the stock, and is defined is defined starting by a process X that is stationary and has in general values in Rd, and a renewal sampling sequence capital T that we assume being independent of X. We can then define our sequence capital Y by using the following definition. We always call X the underlying process in the following and capital Y the renewal sample process. Now that we have introduced a little bit of notations that we are going to use throughout this talk, I would like to present to you the target of our work. So what we can show is that if X is strictly stationary and either weakly dependent or strongly mixing, and the weak dependent or strong mixing coefficients related to the process X have an exponential or power decay, then we can show that our process Y inherits the asymptotic dependence structure of X. This in particular enables the use of the existing asymptotic theory for weakly dependent and strongly mixing processes in the case in which renewal sampling data are at disposal. There are obviously certain kind of conditions under which this statement applies. Please give a look at our paper on archive or at our conference poster if you want to know a little bit more details regarding the conditions under which this statement precisely applies. I will explain in the next slides very briefly how this result is achieved. First of all, what we do in the paper, at the start of the paper, is defining a unified formulation of strong mixing and weak dependence, which is achieved by defining what we call the phi weak dependence. So let us give a little bit a look at this definition. So we have X, that is a process with values in Rd. We have a function capital Phi, that is typically a function from Rs plus to L plus and not decreasing in all arguments. The process X is called phi weakly dependent if there exists a sequence of coefficients J converges to 0 and satisfying the following covariance, the following inequality, in which on the left-hand side of the inequality sign appears a covariance in absolute value, and on the right-hand side it appears a constant that is typically independent of R, the function capital Phi, and our coefficients J. What I would like to attract your attention on is that in this definition we are not explicitly describing the shape of the function capital Phi, neither we are explicitly specifying the set to which the function capital F and capital G belong to. This is because, as I already said, this definition allows to formulate, just using a name, so the phi with dependence, several measures of dependence that are present in the literature, and it achieves this whenever we choose a specific shape of the function psi or specific functional space capital F and G. In particular, the theory that we develop covers the following measure of dependence. So the eta, kappa, and zeta weak dependence, the lambda weak dependence, theta weak dependence, and alpha strong mixing. Once we have this formulation for our measure of dependence, I would like to present to you the central result of our paper, that is the result that shows how, starting by a renewal sample process Y, having an underlying process X being strictly stationary and phi weakly dependent with coefficients I, that it exists a sequence capital E which satisfies the inequality we just saw for the phi weakly dependent process. Moreover, we are capable of determining specifically how this sequence looks like in function of the probability distribution function mu of the sequence of the interarrival times tau. Note that inside this interval, what it appears is the n-fold convolution of the probability distribution mu. However, this is not enough to directly affirm that our renewal sample process has inherited the asymptotic dependent structure of the underlying process X. And this is because this theorem doesn't give us the convergence to 0 when n goes to plus infinity of the sequence capital E. But in the case in which we have this kind of result, so we are capable of computing capital En sequence following this formula, and we can show that these coefficients converge to 0 as n goes to infinity, then by using this theorem, we know that Y inherits the asymptotic dependent structure of X. In the paper, we show that for a special decay rate of the coefficients of the underlying process X, we can easily show that the phi weak dependence is inherited. Let's, for example, consider the case in which the underlying process X has coefficients with exponential decay. Therefore, by using the Laplace transform of the distribution function mu, we can determine an upper bound for the coefficients En that is very, very easy to compute, and that obviously we can show just by looking at it that when n goes to plus infinity, converge is the results we needed to show that this sequence goes to goes to 0. Therefore, in the case in which we work with a process X, so we are sampling a process X that is strictly stationary, phi weakly dependent, and with coefficients that has exponential decay, we can conclude directly that our sample process is phi weakly dependent. We also show in the paper some results regarding the power decay. This means we are assuming that X is strictly stationary, phi weakly dependent, and its coefficient are bounded by the following power. In this specific case, we can show that the coefficients of the process Y admits just asymptotically the following bound. That, however, is enough to show that also in this case, the renewal sample process Y inherits the phi weakly dependence of its underlying process X. This concludes my talk. If you are interested in seeing our proofs or seeing examples of renewal sample processes to which our theory applies, please give a look at our paper on arXiv or at our conference poster. I thank you very much for your attention, and I leave you with this brief bibliography of the talk. Thank you and bye.